To start with, we will define the average velocity. Now, the symbol that we'll use for average velocity is V sub AV. V for velocity and AV for average. And this is also going to be a vector, so we need to put a vector sign on it. We will define this as the displacement over the time interval. In other words, how much time elapsed from R naught to R. So we'll write this as the displacement, which we already have, is delta R, over the time interval. Well, we could write that as delta T. Or we could write this as R minus R naught over T, whatever time it was for the position R to occur, minus T naught, the time at which R naught occurred. So we've got the average velocity is delta R over delta T, delta R vector over delta T, which is R minus R naught over T minus T naught. Now be careful, this is not the same as speed. In physics we will use some terms that are very commonly used in ordinary everyday language, but we will use them with a very, very specific definition. For example, velocity is often used to mean the same thing as speed in ordinary everyday language. However, speed is a scalar in physics. Speed is a scalar. It has no direction. So when you talk about the speed of something, you're talking about how fast something is moving, but without the direction. So it's just a scalar. Velocity is a vector, so velocity must have a direction with it. Speed is actually the magnitude of the instantaneous velocity. How fast is something moving at a particular instant? And we'll come back to that instantaneous velocity in just a minute. But let's start with the average velocity. So let's stick some numbers in here. Let's imagine that we've got our object, let's say, at some initial position, let's say 15 centimeters, at some initial time, let's say 3 seconds, and the object ends up at, let's say, 27 centimeters, at some final time, let's say 5 seconds. So this is T naught is 3 seconds, R naught is 15 centimeters x hat, and then T, the final time, is 5 seconds, and R is going to be 27 centimeters x hat. So what do we get for our average velocity? The average will be R minus R naught, so 27 centimeters x hat minus 15 centimeters x hat divided by T minus T naught. In other words, 5 seconds minus 3 seconds. Then what do we get? 27 minus 15 is 12. 12 centimeters x hat, 12.0 centimeters x hat, divided by 5 seconds minus 3 seconds, 2 seconds. So what do we get? 12 divided by 2 is 6. 3 sig figs divided by 3 sig figs, 3 sig figs, so 6.00. And let's look at our units. We've got centimeters over seconds, so centimeters per second x hat. So we have an average velocity of 6.00 centimeters per second x hat. Notice that the units that we have, centimeters per second, are a distance divided by a time. That's going to be a very, very consistent result. Anytime we have a velocity, we'll have units of a distance per time. Typically, the standard SI unit will be meters per second. So meters per second will be our standard SI unit for velocity. The standard SI unit for the position vector and the displacement vector will just be meters. Now, let's notice. First of all, this is a positive quantity. What is that telling us? Well, positive velocity basically comes from positive displacement. That means it's a positive velocity, means motion to the right. And this is just what we've seen here. What we've got is the net motion is to the right. So we have a positive velocity. Okay, let's stick some other numbers in. Let's imagine our initial position is, let's say, 10 centimeters. 10 centimeters x hat at 3 seconds. And our final position is, let's say, 10 centimeters at a time of 7 seconds. Now what do we have? We have final minus initial, 10 minus 10. So we have 10 centimeters minus 10 centimeters divided by 7 seconds minus 3 seconds. So 7 seconds minus 3 seconds. What do we have? We have 10 minus 10 is 0. 7 minus 3 is 4. 0 divided by 4 is 0. What do we end up with? 0. What is this showing us? Well, I've got these drawn like they're different positions, but these are actually the same position. What do we have? We have our object starting off here and ending up at the same position. The average velocity is 0. Does that mean that there is no velocity at all during that time interval? No, it doesn't. Whoops, sorry about that. Sorry about that. I'll get that later. What does this mean? Sorry. It means that we're starting here, we might be moving around, and ending up back at the same position. The net motion is 0. Wherever we end up is exactly where we started. The net velocity is 0. So, V average, 0. What if let's say we start out at, let's say, some position 35 meters at some time of, say, 3 seconds. So this is R naught and T naught. And then let's say we end up at some position 20 meters. So this is R. At some later time, let's say 8 seconds. Now what do we get? We get an average velocity of R minus R naught, 20 minus 35. So 20 meters minus 35 meters. Need an X hat in there. Divided by T naught minus T, T minus T naught, 8 seconds, minus 3 seconds. What do we get? 20 minus 35, that's negative 15. So we have negative 15 meters x hat over 8 minus 3 is 5 seconds. What do we have? Negative 15 divided by 5, negative 3. So we have negative 3 meters per second x hat. So now we have a negative average velocity. What does this mean? Negative means net motion to the left. So the negative velocity tells us the object overall is moving to the left. Does that mean there is no motion to the right? No. The object might start here, move this way, but then come back here and end up to the left of where the object started. Okay. Very, very good. Let's take a look at a graph like this. Let's imagine that we're going to graph the position, in particular the x variable. Let's imagine we graph the x variable as a function of time for some object undergoing some motion. And it's coming up here any second now. Okay, any second now. Any second now. Here we go. Okay. All right. So here is the motion. Let me turn these lights off just for a second. Okay. So here is a motion. This is kind of a picture of what's going on, and then graphed down here. So first of all, from a time of 0 to 600 seconds, we've got someone riding their bicycle to the right. From 600 to 1,000 seconds, we've got the person taking a break, not moving. And then from 1,000 seconds to 1,800 seconds, we've got them going back to the left. So if we were to graph x, their x coordinate, as a function of time, what do we see? Well, from 0 to 400, their x value is increasing. At 600 seconds, they are not moving, so their x value remains constant. And then from 1,000 seconds onward, what happens? They're moving to the left, their x coordinate is decreasing. So we end up with a graph that looks like this. Anytime we have straight lines on a graph, sometimes it's useful to figure out what the slope of the graph is. If we were to look at the slope of this, how do we find the slope of a line? We pick 2 points. We find the change in the vertical axis divided by the change in the horizontal axis. So let's pick this point and this point, a time of 200 seconds and 400 seconds, and a position of 400 meters and 800 meters. The change in the horizontal axis is 400 minus 200, or 200 seconds. Change in the vertical axis, 800 minus 400, or 400 meters. What's the slope? It's going to be delta x over delta t, 400 meters divided by 200 seconds, 2 meters per second. But what is that? Delta x over delta t, that's nothing more than the magnitude of the average velocity. So the slope of the line gives us the average velocity of the motion. Notice, this is positive. The person is basically moving to the right at 2 meters per second. What's the slope here? Well, in this case, what is delta x? There is no vertical change, so delta x is 0. What is the average velocity here? Delta x over delta t. The average velocity over this section is 0 because the person is not moving. The line is horizontal, 0 slope, 0 average velocity. What about over here? In this case, x is decreasing. So our final position is 400, initial is 800. I'm sorry, other way around. Final is 400, initial is 800. 400 minus 800 is negative 400. So delta x is negative 400 meters. What do we get for the slope? Change in the vertical is negative 400 meters divided by 400 seconds, or negative 1 meter per second. So in this case, the average velocity is negative. When the person is moving back to the left, we end up with a negative average velocity, a negative slope. So the slope of a line of a plot of the motion, plotting position on the vertical axis, time on the horizontal axis, gives us, the slope of that line gives us the average velocity of the object. Now, do we have to pick 2 points? Notice that for each of these we had to choose 2 points to figure out the slope. Anytime you figure out the slope of a line, you need 2 points. Change in vertical over change in horizontal. Do we have to pick 2 points on one straight line section? No. We could pick, say, this point and this point over here and figure out what's the average velocity between these 2 points. Well, in that case, what would we get? We'd get, say, 200 seconds and 1,400 seconds. That's a difference of 1,200 seconds. What's the difference in position? Well, we end up at 800 meters. Initially 400 meters, 800 minus 400 is 400. So we'd have 400 divided by 1,200. What's that? That's 4 over 12, or 1/3, about 0.3. We end up with an average velocity of 0.33 meters per second, positive. Now what's that telling us? That's telling us the average velocity of the object, of the bicycle rider, from this point in his motion, to this point in his motion. That's the average velocity of the overall motion from here to here, and that basically gives us the slope of a line segment if we were to draw it in here. Even though the rider doesn't actually ride along this line, we can still define the average velocity between those 2 points. Okay, let's put this back up. So far, we have been looking at motions. We've been choosing points for objects that are basically undergoing straight line motion or combinations of straight line motions. uniform velocities. What if we have a motion where if we were to graph the motion, say, x as a function of t, let's say the motion looked something like this. So a smooth curve as opposed to straight lines or combinations of straight lines. Could we define an average velocity for this type of motion? Well, sure. We can pick 2 points, any 2 points we want. Pick a point here, and let's say a point here. We find the time and position of that point, the time and the position of that point. We find delta x. Delta x will be this value. Delta t will be this value. So here's delta x, here's delta t. The slope, delta x over delta t, basically then gives us the slope of the line segment that joins one point to the other. Now notice that the object does not actually travel along that line. It travels along this curve, the green curve, but we can certainly find the average velocity, which would be the slope of the line segment that joins the 2 points, the red one, from here straight up to that one. Okay. Now, if you are out driving your car or something like that, you might be speeding up slow. No, well, I'm sorry, let me back up 1 second. So what would this motion look like? Well, this motion is actually motion that's, this graph describes a motion of something that's speeding up. So something that's moving slowly and then going faster and faster and faster. So something that's speeding up, changing its velocity. It doesn't have a uniform velocity. It's changing its velocity. If you are driving your car and you are starting out and you're maybe pulling onto the highway or something, you're going slowly at first and then you speed up and go faster and faster and faster. If you look at your speedometer tells you how fast you're going at a particular instant. Say right now you're going 20 miles an hour, and then you're going 30 miles an hour, and then you're going 40 miles an hour. So the speedometer is telling you how fast you're going instantaneously at a particular instant. Not an average over some long section of the highway, but how fast are you going right now, or right now, or right now. Well, how might we get an idea of something like that? How might we define how fast something is going instantaneously? Now obviously this average velocity gives us kind of an average measure of how fast an object is going between these 2 points. If we were to make those points closer and closer, so perhaps rather than so far apart we choose a point here and a point here, that slope might give us a better idea of what's going on here. Or if we pick a point here and here, that gives us a better idea of what's going on there. The closer we can bring these 2 points, R and R naught, the closer we get those two together, the closer that average velocity is going to be to how fast the object is going between those 2 points. So imagine like you're driving down the highway, if you pick 2 times very close to each other like now and now, if you could determine the average velocity over that time interval, that would be a much better approximation as to how fast you are going instantaneously than if you were to choose a time, say, now, and a time, say, now. If they're very far apart, your velocity might be changing much more, and the average might not really indicate how fast you're going at an instant. So let's imagine that we bring these 2 times closer together. Let's imagine we keep this time right here, so we'll keep T naught and R naught right there, but let's imagine that we bring our final time, we bring the final time closer and closer to the initial time, so this point gets closer and closer and closer to our initial time, so this line segment gets closer and closer and closer to something that's very close to our curve. What we end up with is actually figuring out the slope of a line segment that's tangent to our curve. So if this point gets closer and closer, this segment gets closer and closer to a tangent to the curve. Now, if that doesn't make sense, that's okay. We're just going to use this idea to give us an idea of how to define the instantaneous velocity. We will only use this idea one time later on in the semester But I just want you to have an idea of what we're talking about when we mean an instantaneous velocity. We mean an average velocity over a very, 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 very tiny time interval. Essentially, we want to let that time interval go to 0. So, to write this out mathematically, what we're going to do is we're going to take our average velocity, which we have as delta r vector over delta t. And we're going to let this time interval get very, very small. Mathematically, we write this as the limit that delta t goes to 0. So imagine we're letting this time interval get closer. The 2 points get closer to each other. So I'll write here, limit as delta t goes to 0. This is then how we will define v without the average, and this is what we mean by the instantaneous. Instantaneous velocity. In other words, how fast is an object going at a particular instant? We're going to use that definition. We're not going to implement this definition mathematically, except for one time, as I mentioned, later on in the semester. Then we'll use this limiting idea.